In this video, we're going to take a look at extreme values. So we're going to look at extrema, and I'm going to start out talking about absolute extrema. All right. So let's say we have a function, and the function is going to be a function where z is equal to f of x, y. So we have inputs from R2, and that's going to generate out a surface in R3. And we're going to let that function be defined on a set containing point P. If, when I plug in P, I get an output value that is greater than or equal to all other output values when I plug in any other point in that set, then we say f, the function f, has an absolute maximum at point P. If by plugging in P, I get an output value which is less than or equal to the output value when I plug in any other point from the set, then we say f has an absolute minimum at P. So basically, if you think about this as a surface, what we're saying is that plugging in P is giving us the highest point on that surface. Then we get an absolute maximum at P. If by plugging in P, I get the lowest point on that surface, then I have an absolute minimum at P. Now, an absolute minimum or an absolute maximum is called an absolute extrema. So if f has an absolute maximum or an absolute minimum at point P, then we say f has an absolute extrema at point P. So extrema means either a maximum or a minimum. Absolute means it's that way for every, it's that way in wherever we're defining my function on, in whatever set I'm defining my function on. Now, we can also take a look at relative extrema. So we'll take the same assumptions we had in our last slide. And a relative extrema is going to be a little bit different. If there is an open disk D containing the point such that the output value is the maximum amongst all points in D and in S, where we're defining the function, then we say f has a relative maximum at P. So in other words, it might not be the maximum amongst all points from our overall set, but it's the maximum in that local region, in that little open disk. And similarly, if we can find an open disk containing P such that the output value of your function when you plug in your point is less than or equal to the other output values around it, then f has a relative minimum at P. So we have a relative maximum. If it's the maximum around that area. We have a relative minimum. If it's the minimum around a specific area. And a relative maximum or a relative minimum is a relative extrema. So if f has a relative maximum or if f has a relative minimum at point P, then we say F has a relative extrema at point P. So maximum or minimum can be relative or absolute. Absolute means it's the highest or lowest point amongst everywhere where we're defining it, everywhere in set S. Relative means it's the maximum or the minimum around a small area, some open disk. Now, it should be clear that if we have an absolute maximum, an actual achievable point that's an absolute maximum, then it's also going to be a relative maximum. If we have an absolute minimum, then it's also going to be a relative minimum, because if it's universally, if this equation holds universally, then it's obviously going to hold in an open disk around that point. Now let's take a look at the concept of a critical point. Let's let a function be continuous on a set S. Again, we're just defining some set S. A critical point, we'll call it P again, of my function is a point in S such that when you plug in P to the first partial derivatives, you get 0 for both first partial derivatives. Or if you plug it in to the first partial derivatives, at least one of those is undefined, and possibly both. So a critical point deals with the first partial derivatives. If both first partial derivatives are 0 at the point, then the point is a critical point. If either one of our first partial derivatives is undefined at point P, then we say we have a critical point. All right. Now, why do we care about these equations? Well, we care about those equations because there's a connection between our relative extrema and our critical points. Assume the same assumptions we usually do. We have a function with inputs from R2 defined on some open set containing point P. We say that, well, we know the connection is if my function has a relative extrema at point P, then point P is a critical point of my function. So if we have a relative extrema, then the point is a critical point of F. So we're going to use that fact to find our relative extrema. We're going to find the critical points of F and then determine if or maybe which ones are relative extrema. So relative extrema have to occur at critical points. Some critical points are relative extrema. There, we'll see later that there are other critical points that are not. But we look for critical points and then we determine if they are relative extrema or not. And the way we're going to look for critical points is essentially by these equations. We're going to see if my first partial derivatives could be undefined. If they can, we'll figure out where they can be undefined. If they can't be undefined, then we'll see when can they both be equal to 0. And if they can both be equal to 0 at the same time for a specific point, then we'll know that we have a critical point at those value at that point. So let's take a look at this example. This is a function that we've seen before. We're going to try to find the critical points of f, and then we're going to determine the relative extrema of f. So we're going to find relative minimums and relative maximums if they exist. The function that I'm looking at is x squared minus 2x plus y squared minus 3, a function that we've graphed a number of times. So I'm going to start by taking the first order partial derivative with respect to x, and then I'll take the first order partial derivative with respect to y. First order partial derivative with respect to x is 2x minus 2. First order partial derivative with respect to y is 2y. Now, there's no way that either of these two can be undefined. You can plug in any x you want and get out a value, plug in any y you want and get out a value. So plugging in any point into either of these two is going to be fine. So the only way I can get a critical point is when both of them are 0 simultaneously. So 2x minus 2 has to be 0, and 2y has to be 0. So we can solve this system of equations for x and y. And it's fairly easy to do because our first equation only involves x, and our second equation only involves y. So this system of linear equations is pretty easy to solve. It's not always going to be linear equations you'll have, but in this case it is linear equations. So this system of equations yields that we get a critical point when x is 1 and when y is 0. So we have a critical point of 1, 0. So that's a critical point. Now, I'm going to look up on the graph and show this. Obviously, we've done this before, but I'm going to remind you, if you plug in 1, 0 into your function, if you plug in 1, 0 into your function, you get a negative into this original function I'm talking about. You get a negative 4. So we'll show that graphically, how this critical point works out, where it's at. And again, I'm sure you've seen it before. All right, so again, this should look familiar. We have this elliptic paraboloid pointing up, and the point 1, 0, negative 4 is that very bottom point. And we know the f sub x and the f sub y give me 0. That means the directional derivatives, well, the directional derivative in the x direction had slope 0, in the y direction had slope 0, and any directional derivative actually has slope 0. So that's the point. And just visually, we can see that this point is a minimum. So this point, visually speaking, is a relative minimum. And in fact, it's an absolute minimum because this pattern goes on forever up. So we have a relative minimum point. In this particular case, this relative minimum is also an absolute minimum. Okay, but the question just asked whether it was a relative minimum or a relative maximum. So I'm going to just state it's a relative minimum. So we have a relative minimum at 0.10. Okay, we saw that visually. Now, we'll see later that there's actually algebraic methods to decide when we have a relative minimum or a relative maximum or something else. So we'll see some algebraic methods later of how to figure that out. But for right now, our graph will do. We can see we have a relative minimum at that critical point. So hopefully finding critical points makes sense. Again, if you can't see relative minimums, that's perfectly all right. We'll find some algebraic methods to determine when we have minimums, when we have maximums, when we have other things in just a little bit later on this video. Let's take a look at this example. This is example 2. We're going to find the critical points and then determine the relative extrema of our function. Our function is x squared minus 6x minus y squared plus 8y. So we'll do the same thing we did in the previous case. We'll use the first partial derivatives, first partial derivative with respect to x, first partial derivative with respect to y, to find critical points. All right, so let's take a look. F sub x is going to be equal to 2x minus 6. F sub y is going to be equal to negative 2y plus 8. So there we go. Now, again, no matter what point you plug in into your partial derivative with respect to x, you're going to get out a value. So it's going to be defined everywhere. Same thing with f sub y. No matter what point you plug in, you get a defined value. So there's no undefined first order partial derivatives. So in order to find the critical points, we're going to set each of those equal to 0, and that's going to create a system of equations. Again, in this case, it's going to be linear equations, but it doesn't always have to be linear. And this system of linear equations has only one solution. And that solution is the point 3, 4. So we get one critical point at the point 3, 4. Be careful about that. Sometimes people think, well, I can plug in any x here and get 0. Or to me, not any x. I can plug in 3 here for x and get 0. And I can plug in any y I want in this first equation. Or they'll look at the second equation and say I can plug in y of 4 with any x I want. But remember, the rule is to be a critical point, both equations have to be equal to 0 at the same time. So the only critical point we get is the point 3, 4. And this is going to happen a lot where you might only get one critical point. Just like in the previous problem, we only got one critical point. So we got a relative minimum in the previous problem. There was no relative maximum for that function. So there's no relative maximum for the function in the previous problem. In this case, my critical point 3, 4, just so that when I graph this, it'll be nice. If I plug in 3, 4 in my original function, in this function here, I would do 3 squared minus 6 times 3 minus 4 squared plus 8 times 4, and that would give me a 7. So we're at the point 347 in R3. Now, I'm going to, again, visually determine what this critical point is, whether it's a relative minimum, a relative maximum, or something else. So I've graphed this function along with the point so I can visually see it. Now, it's kind of off of my graph right now, but if I scroll out a little bit, scroll so that my X, Y, Z axis a little bit heavier, I can see this point there. Notice that if I look at it in this direction, we can clearly see that if we're moving in the X direction, left or right, this point would move up. However, if we're moving in the direction of Y, left or right along the Y-axis, parallel to the Y-axis, then the point is going to be moving down. So this is neither a minimum nor a maximum. If I draw a little circle around here, I can find, so draw a little circle here. I can find points that are above the purple point or below the purple point by just moving in whatever direction. If I want to find a point above, I move in the direction of X. And as you move in the direction of X, you kind of move this way. Let me show that. In fact, I'm going to do it slightly different. I'm going to call that G. So let's put our point, match it up. So we're at the point 3, 4. And as I start moving this, oh, I didn't hold on. That's better. So I want to be at the point A, comma, B, comma, my function value. And if we're at the point 3, 4, then we're right on top of the point. And as you move in the Y direction, you move down. Again, Y direction, I just mean parallel to the Y axis. So as you move in the Y direction, you go down. But if you move in the X direction, you move up. This point, this 3, 4, 7, is what's called a saddle point. And it's called a saddle point because if you look at it, it kind of looks like a saddle. Like if you sat on this point with your legs off to the left, your legs would be going down, pointing down. And then you would be facing this front direction towards X. And the part in front of you and behind you would be going up. So imagine sitting here with a leg dangling over each side. In front of you and behind you, we'd get an up curve, but to the side, we'd get a down curve. This is known as a saddle point, and a saddle point is a critical point, which is not a relative minimum and also not a relative maximum. So a saddle point is neither relative max or relative min. So we say the point 3, 4 is a saddle point. Okay, so that's the idea of a saddle point. Now we'll define that on the next slide here. So a point P, we're going to assume is in the domain of my function, and we're going to assume the first partial derivatives, one with respect to x and one with respect to y, are both 0 at the point P. We say P is a saddle point of F if for every open disk containing P, there are points such that plugging in a point gives you a value bigger than the output. When you plug in P, that's this one, that's the second one, excuse me. So plugging in a point, so there's some points that are bigger or have higher output, and then there are some points which have smaller outputs. That one. So if we find a critical point such that, well, for every open disk, there's some values which are bigger and some values which are smaller, then we get a saddle point. Now, the way we've done this on the first two examples, when we determined the relative minimum versus relative maximum versus saddle points, we just looked at the graph. But that's not a very easy way to go about things because oftentimes it's hard to graph a surface or it's hard to scale appropriately so we can accurately see what's going on. And if we can't accurately see what's going on, then using the graphing tools in 3D aren't going to help us very much. So we have something called a second derivative test. Now, it's going to take a couple of slides to explain this, but essentially what we do is we take the second partial derivatives of my function. Obviously, I have to have a function where those second partial derivatives are defined for this to work. And when we have a critical point, what we do is we plug in that point into our second partial derivatives. I'm going to take f sub xx multiply it times f sub y. This is after I've plugged in the point. And then I'm going to subtract f of xy squared. So I get the f sub xx times f sub yy. And this you could have rewritten as f sub xy times f sub yx. But remember, we know those are going to be the same, so we can just square f sub xy. So we calculate this thing, which traditionally we call D, capital letter D. And here's what happens. If that D is positive and f sub xx is positive at point P, then f has a relative minimum at P. If D is positive and f sub xx is negative, then f has a relative maximum at P. If the D is negative, then f has a saddle point at P. And the only other option is when D is 0. If D becomes 0, then the test is inconclusive. So if we can find these second derivatives and determine whether that D is positive and the f sub xx is positive, if the D is positive and the f sub xx is negative, we can determine relative minimum, relative maximums. If the D is negative, we know it's a saddle point. If D is 0, then our test is inconclusive. Okay, so this is an algebraic way to figure out what type of critical values. Now, we can't just go ahead and plug in any P into this. These P's, remember from the last slide, we have to start with a critical point in order for this test to make any sense. If we don't have a critical point, because of this relationship, if you don't have a critical point, then there's no hope for a relative extrema. So this is only going to be a test which we can use for critical points. And we calculate this D at whatever point we're looking at. And then that test, this test here, determines what type of critical point it is. A relative minimum, a relative maximum, or a saddle point. Now, before we move on, I wanted to just go ahead and do this second derivative test for the two functions we've already dealt with. So we found critical point of 1, 0, and we've visually seen that it's a relative minimum. If I want to figure out algebraically that that was a relative minimum, again, we've found it already. We have this critical point. Let's say I didn't know. Let's say I didn't have any graphing calculator that can do a three-dimensional graph. What I would do is I would take f sub xx, that's a 2, f sub yy, that is also a 2, f sub xy is a 0. Now, these turned out to be second derivatives that were constant, but If you'd have plugged in 1, 0 into these second derivatives, you just get 2, 2, and 0. That means the D, which remember was f sub xx at the critical point, times f sub yy at the critical point, minus f sub xy squared, f sub xy at the critical point squared. What we end up getting for D is 2 times 2 minus 0. So we get a 4. The f sub xx is positive. The D is positive. So based on what we saw before, we have a relative minimum at the critical point 1, 0, since, like I said, D is positive, 4 is greater than 0, and f sub xx at the point is also positive, greater than 0. Now you might think like, why does this test work? And this is not a perfect analogy, but I'm going to kind of use this analogy. Notice that if D is positive, then the f sub xx times f sub yy is overpowering this f sub xy squared. Okay? And they're both the same sign. So in this case, both were positive. So what that means is the second derivative with respect to x is positive. The second derivative with respect to y is positive. If you remember back to earlier calculus courses, second derivative being positive means we are concave up. So we're concave up in the x direction and also concave up in the y direction. If I were to draw this, that means I'm concave up in the x direction, and then in the y direction also concave up. So if you're concave up in both those directions, then what you're getting is a minimum value. Now, on the other hand, if both of those were negative, so you ended up with a D that was positive, but both the f sub xx and the f sub yy were both negative, then you'd be concave down in both directions. And so you end up with a relative maximum. And if one of these is negative, one of those is positive, then you get concave down in one direction and concave up in the other direction. And that's where you get your saddle point scenario. So that's kind of what's going on. Again, my drawings right there are not very good, but we can see kind of why this goes on in the graph. Now, before I turn to my graph and look at this example, let's calculate the D in this scenario, the second scenario, my example 2. The way we do that is we take the second derivative with respect to x. In this case, that's 2. Then we take the second derivative with respect to y. So f sub y, that's a negative 2. And then we take f sub xy. That becomes 0. So the D is going to be 2 times -2 minus 0 squared, which is -4. D being negative meant that my critical point, when I plug in the critical point, obviously these are constants. So when you plug in the critical point, you're going to get those exact numbers. But D being negative means the 0.34 is a saddle point. All right. So there you go. Negative D means saddle point. Positive D means either you get a maximum or a relative maximum or a relative minimum. And depending on what f sub xx is, it could be a relative minimum or a relative maximum. And again, these are two good examples of looking at what we're actually achieving here. If you look at this point relative to x, you can see the curve in the x direction that outlines my elliptic paraboloid is concave up. So it's pointing up as we're orienting in the x direction. As we've oriented in the y direction, also we're concave up. So since we're concave up in the x direction and in the y direction, this is a relative minimum. On the other hand, in my second function, you could see in the y direction, we're concave down. As you move in the y direction, your point's moving down. But as you move in the x direction, both left and right, you're concave up. So in the x direction, you're concave up. The y direction, you're concave down. And you end up with a saddle point. You end up with a negative D, which says it's a saddle point. All right, so let's look at another example. We're going to find critical points and use the second derivative test to determine if each of the critical points corresponds to a relative minimum, a relative maximum, or a saddle point. Our function in this case is x squared plus 3y squared minus 6y plus 4xy. So we got to find the critical points and then use the second derivative test to figure out what those critical points are. Let's go ahead and do that. All right. So what I like to do is I like to first off find the critical points. So take the first partial derivatives. F sub x is going to be 2x plus 4y. F sub y is going to be 6y minus 6 plus 4x. Now, that's going to give me a set of equations, 2x plus 4y equals 0. Again, both of these have to be 0 at the same time to get critical points. There's no way they're going to be undefined. No matter what point you plug in, you're going to get a function, the function is going to be fine. You can get a value out. So the function is going to be defined no matter what you plug in for both your f sub x and f sub y's. So the only way we can get a critical point is if both f sub x and f sub y are 0. Now in this case, if I set f sub x equals 0, I get 2x plus 4y equals 0. If I set f sub y equals 0, I get 6y minus 6 plus 4x equals 0. I'm going to reorder that. I'm going to write 4x plus 6y minus 6 equals 0. Because what I want to do is I want to solve this system of two equations. So I have two equations. I need to solve the system of equations. This is just basic solving a system of two linear equations. I need to get opposite coefficients on one of those. So I'm going to multiply this first equation by a -2 on both the left and the right. I'm just going to write it this way. Both sides, I got to multiply by -2. And then on the second equation, I'll add 6 to both sides so everything lines up. I'm using the elimination method in solving this. So you get -4x minus 8y equals 0 for the first equation. And for the second equation, you get 4x plus 6y is equal to 6. Now the elimination method says that now that I have opposite coefficients on my x of 4 and -4, I can add those two equations together. I'll add the x components, that's -4x plus 4x, gives me 0x. Then add the y values, -8y plus 6y gives -2y. The equal sign needs to line up, so still becomes an equal. And then 0 plus 6 becomes 3. I'm sorry, it becomes 6. When I divide by -2, I can see that y is -3. Now that I know y is -3, I can plug it in into either my initial equation or this initial equation. So either initial equation will work. Either my first equation or my second. I'll use the first equation. Once I've found y has to be -3, I plug it in there. We'll get 2x minus 12 is equal to 0. And it's pretty clear that x has to be 6. Notice that the point 6, -3 is the only point that makes this system of linear equations true. So we only get one point that works, and that is the point 6, -3. So we get one critical point. One critical point, and it happens at the point 6, -3. Now, we want to figure out whether that critical point is going to give me a relative minimum, a relative maximum, or a saddle point. So I need to take the second derivatives, f sub xx, second derivative, both with respect to x, is going to give me a 2. F sub yy, second derivative, both with respect to y, gives me a 6. And f sub xy, when I take that derivative, I get a 4. Now, here's why it's so important to do the test. Our test, remember, is by taking f sub xx at the critical point times f sub yy at the critical point, and then subtracting f sub xy squared, that f sub xy is calculated at the critical point. So for this d, we end up with 2 times 6 minus 4 squared, which is 12 minus 16, which is a negative 4. So that means that critical point of 6, negative 3 was actually a saddle point. So we get a saddle point at 6, negative 3, as long as I've done my calculations right. Just as a note, this is why the D is so important, rather than just by looking at f sub xx and f sub xy. You might have concluded that since it looks like it's concave up in the x direction and concave up in the y direction, that, oh, concave up, you might think, oh, that means I should get a relative minimum. But this mixed partial being 4 is big enough that it actually throws my point into a saddle point. Let's go ahead and graph this and see if we can visualize what's going on. So I've graphed the function and I've graphed the critical point. Well, the function gives you a surface that looks like this. And so if you're looking at it straight on in the x direction, it's looking one way. If you're looking at it straight on in the y direction, it's looking similar, but as you look at it in sort of along this plane, it looks very different. But we can clearly see visually that this is a saddle point. There are some points around this green value which are below it, and there are some points around the green value which are above it. So pretty easy visually to see, but again, you won't always have that visual. So the algebraic approach gives us a determination of relative minimums, relative maximums, and saddle points. And clearly, algebraically, this was a saddle point, and we can confirm that using this calculator. Let's do another. Let's take a function that is 1/2 x squared times y squared, and let's try to find critical points and then use the second derivative to determine which ones are relative minimums, which ones are relative maximums, and which ones are saddle points. Now the function here, obviously, that we're dealing with is 1/2 times x squared times y squared. So we're going to have partial derivatives which work differently than they had before. So f sub x is going to be, well, I'll take the 2 out front, so that's 1/2 times 2. I get 1 x to the first times y squared. F sub y is going to be 1 times x squared times y. There's no place at which these are undefined. So we ask ourselves, when are both of these equal to 0? So when are both of those equal to 0? And you may see this and say, I hope you see this and say, well, actually, there's a lot of places that both of these are equal to 0. Anytime I have an x value that's 0, I'm going to get both of these being 0. Anytime I have a y value of 0, I'm going to get both of these being 0. So we're going to have infinitely many critical points. So critical points of any x value being 0, along with any y value. And we also get a critical point with any x value where the y value is 0. So we get infinitely many critical points. By the way, one of these has to be 0 in order to get 0 when I multiply. So critical points of 0 comma y and x comma 0 for any x or I should say any y because I put the y one first. Hopefully that makes sense. So 0, 1 is a critical point, 0, 3 is a critical point, 0, negative 80 is a critical point, 19 comma 0 is a critical point, 83 comma 0 is a critical point, negative 24 comma 0 is a critical point. So for any values there, we get critical points. So let's see what kind of critical points these are. Let's take the second derivatives. Second derivative with respect to x is going to give me y squared second derivative with respect to y, both with respect to y. So I'm using, again, the first one, xx, I used this first partial. With yy, I'm going to use this partial and take the derivative with respect to y. So I'm going to get x squared. And then my mixed partials, f sub xy or f sub yx, I'd take the derivative of this with respect to y or the derivative of this with respect to x. I'll get the same thing. I'll get 2 times x times y. All right. So what is d? Well, my d is going to be y squared, that's f sub xx, times x squared, that's f sub yy, minus 2xy quantity squared. I'm going to simplify that a little bit. That's x squared times y squared minus 4x squared times y squared, which is negative 3 times x squared times y squared. So here's the weird thing. Let's make this a little bit bigger. Should be 14. There you go. So here's this weird thing. At any of these critical points where I have 0, comma y, if I plug in 0, comma y, I get 0. At x, comma 0, I plug in 0 for y, I get a d value of 0. So all critical points yield a d value, which is 0. And so the best I can do for this one is say I have a lot of critical points, but I don't know what they are. The test is inconclusive for all of my critical points. Now we could try to look at the actual graph. And so let's go ahead and do that. We'll look at the graph of the function. So when we have this function, I've graphed it here in red. We'll zoom in just a little bit. So here's what it looks like from above. It kind of looks like a cross section. Um, and on the side, it kind of looks like just a big wall going up. Now, this graph, while the test was inconclusive, it does look like we're getting minimum values along the x and y axes. That's when x was 0 or y was 0. When x is 0, you're along the y-axis. When y is 0, you're along the x-axis. So it does look like I'm getting minimum values here. I'm getting all relative minimums for my critical points, but my test, again, was inconclusive. But it does, again, visually look like I'm getting minimums. Now, if I asked a question and the test was inconclusive, that would be an option. Would you just write test is inconclusive and kind of move along your merry way, so to speak. But yeah, visually we can kind of see that these are minimum values along the axes. So there you go. Again, if I were to ask a question personally about this, I would ask, well, what's the test say? Oh, the test is inconclusive, and that would be enough, and then you'd move on to the next question. Other instructors might not. do that. So that was this example. We got lots and lots of critical points, and our test was inconclusive for every critical point that we found. Let's take a look at another example. Let's take a function x to the fourth minus 18x squared plus y to the third minus 75y plus 12. And we're going to find the critical points, and then we'll use the second derivative test to determine if each of the critical points corresponds to a minimum, a maximum, or a saddle point. That is a relative minimum, a relative maximum, or a saddle point. All right, so we have a higher degree equation that we've dealt with before. Or I should say in my first two examples, higher degree than those. But nothing really changes. F sub x, first partial derivative with respect to x, is going to be 4x to the third minus 36x. And I think that's it. Yeah, all the other terms go to 0 when I take the derivative. And f sub y is going to be 3y squared minus 75. Those are two equations, and they both have to be 0 simultaneously. So we have 4x to the third minus 36x. That has to be 0. And 3y squared minus 75 also has to be 0. We're going to solve these individually. Let me take this first one. Since the first equation only has the variable x and the second equation only has the variable y, I can solve them independently. So let's do the first equation, 4x to the third minus 36x set equal to 0. I would factor out a 4x and get x squared minus 9 equals 0. And then I'd factor the x squared minus 9 into x minus 3 times x plus 3. Hopefully that was all right. This gives us three options for x. X is equal to 0, x is equal to 3, and x is equal to negative 3. All three of those would make the first equation equal to 0. Now let's look at the second equation. 3y squared minus 75 is equal to 0. First off, I'd factor out a 3. I'd get y squared minus 25 times 3 is equal to 0. Then I'd factor y squared minus 25. Hopefully we know that that's going to be y minus 5 times y plus 5. We're going to set that equal to 0. And so I end up with two y values that would make that second equation 0. Y equals 5 would make that second equation 0, and y equals negative 5 would make the second equation equal to 0. Now, how many critical points are there? Well, I have 3 options for x and 2 options for y. if you plug in any of these three options for x and any of these two options for y, you will end up getting 0 in both the first order partial derivative with respect to x and also the first order partial derivative with respect to y. So how many critical points are there going to be? There's going to be 6 different critical points in this case. There's going to be the point 0, 5. There's going to be the point 0, -5. There's going to be the point 3, 5. There's going to be the point 3, -5. There's going to be the point -3, 5. And last, there's going to be the point -3, -5. So we have 6 different critical points because each of the combinations of x values and y values worked in this case. Now let's go ahead and do a second derivative test. Now we're going to have to do it for every single one of those points, but that's okay. So I'm going to get a different slate so it's a little bit easier. Let's do the second derivative, both with respect to x. We're going to get 12x squared minus 36. Second derivative, both with respect to y, is going to give me 6y to the first. And then the mixed partial derivatives, let's go f sub xy. So you do x first, and then take the derivative of this with respect to x, you get 0. Also, if you did x, y, x, take the derivative of this with respect to x, you get 0. So the value of d is going to be 12x squared minus 36 multiplied times 6y minus 0 squared. I'm not even going to write the minus 0 squared because that's not going to do anything to us. So that's the value for d. Now I have to check that for every single point. I have to do the same. I need to find d, and if d is positive, then I'll also have to find f sub xx at the point. So we're going to do that 6 different times. We're going to say, what's d at the point? At 0.05, d, well, when I plug in 0 for x and 5 for y, I get negative 1,080. F sub xx, when I plug in 0, 5 into that function, well, that's a negative 36. Now, what's this mean? Well, d as negative, that means 0, 5 is a saddle point. There we go. I didn't really even need this piece. I didn't need to plug it into f sub xx. That was perfectly fine without it. Let's do another point. So at 0, -5, some people will use the notation d and then inside of parentheses put 0, -5. I don't like to do that. So I'll just write at that point, d is equal to this. Again, we're going to be taking 0, plugging that in for x, but this time I'll plug in a -5 for d. So we get -36 times 6 times -5. We get a positive 1080. And f sub xx at the point 0, -5 is going to be -36. So d is positive, but f sub xx is negative. Think concave down, so we're getting a relative maximum. So at 0, -5 gives a relative maximum. Hopefully that makes sense. Try and do this on one line. Okay. And we just have to go through all of our points. So all of our critical points. We have 1, we've done 2 now. Now let's go on to 3, 5, and then we'll go on to 3, -5. So I'm going to do a copy and paste so I don't have to rewrite everything every time. Let's do 3, 5. We'll calculate D. So we take 12 times 3 squared minus 36 multiplied times 6 times 5 gives me 2,160. That's positive. So let's plug in 3, 5 into my XX. That's going to be, again here, 12 times 3 squared minus 36. That's 72. So we get positive D. F sub XX is positive, so that's concave up. That means that point gives a relative minimum. Now let's do 3, -5. There we go. So we're going to do 3, -5, and we'll calculate the D first. Plug in 3 for X, and then a -5 for Y. If you do that, you get negative 2,160. At this point, I don't even care what that second derivative is when you plug in 3, -5. It's actually going to be 72, but it really doesn't matter because the D is negative. So 3, -5 gives a saddle point. Anytime D is negative, we get a saddle point. Now let's look at the -3, and we'll do -3 comma +5 first. So -3, +5. -3, +5. Whoops, I miswrote that too. At 3, +5 there. All right. So yeah, I miswrote that. Again, plug in -3, 5 into the D. If I plug in -3, 5 into the D, 12 times the quantity -3 squared minus 36 times 6 times 5, I ended up with, again, 2,160. So D is 2,160. When I plug in -3, 5 into my f sub xx, 12 times -3 squared minus 36 once again becomes 72. So we get a positive D and a positive f sub xx, that's concave up. That means I have a relative minimum at that point. The last point we'll check is -3, -5. -3, -5. So let's plug this in. First, plug it into D. It turns out when you plug that into D, you'll get, again, -2,160, just like we got at 3, -5. And it really doesn't matter. I know this is going to give a saddle point no matter what happens at f sub xx. D is negative, we get a saddle point. If you wanted to calculate this, you'd also get a 72. But again, I don't have to calculate it. Once I know D is negative, that's all I need to know I have a saddle point there. So there we go. We have 6 critical values. We get 1 relative maximum. We get 2 relative minimums. And we get 3 saddle points for this function, this original function here. So that's a fairly interesting and also um, you know, an example with a lot of different critical points. Now, I'm not going to graph this example. We see that we get the 6 critical points. If you wanted to view that example, you could. It's tough to graph because you get points that are with really, really large or very, very small z values. So on Desmos, when you zoom in and zoom out, sometimes that's hard to see. So instead of showing you the graph of this, we're just going to go to the next example, and that's this one. Let's find the critical points of the function y times e to the 3x, and then use the second derivative test to figure out if those critical points are relative minimums, relative maximums, or saddle points. All right. So basic idea is always the same. Take the Derivative with respect to x. First, that is going to be y times e to the 3x multiplied times 3. So we get 3y e to the 3x. Derivative with respect to y is just going to be 1 times e to the 3x. I can plug in any value I want into x and y, so there's no values I can't plug in, no values where f sub x or f sub y is going to be undefined. So I set those two things equal to 0, and then solve these two equations. And I ask myself, what values of x and what values of y can I plug in so that both of these equations are 0? Now, here's the trouble with this one. If you have e to a power, unless we're allowing values of infinity, unless we're allowing ourselves to use limits at infinity, we cannot get e to a power to be equal to 0. Normally, if we would solve this, we'd take natural log of both sides, but if you take a natural log of 0, it's undefined. Therefore, what this means is there's nothing we plug in that gives us an undefined f sub x or f sub y. And there's also nothing that can give us f sub y to be 0. Therefore, there are no critical points of this function or for this function. And essentially, there's nothing to do from there. We say we want to define the critical points. Well, there are none because we cannot solve that second equation. There's no x we can plug in that's going to give us a 0 in that second equation. There are things that we can solve for in the first equation. Anytime you plug in a 0 for y, the first equation can be 0. So you can solve the first equation. That's fine. The second equation is the troublesome one. So there's no value of x you can plug in to get that second equation to actually be true. So therefore, there's no critical points, and there's no relative minimums, there's no relative maximums, there's no saddle points in the graph of this surface. Let's actually take a look at this and confirm that. Confirm that we don't see any relative minimums, relative maximums, or saddle points. So here we have our surface. It's a very interesting looking surface, but you can see that if I have a point on the surface, no matter where I put it, there's going to be points above and points below, immediately above and immediately below. If I move that to some other place, let's say we move it here, there's other points near it that are above and other points near it that are below. even if we move that over here, well, it might not look like it. There is a little bit of increase as I move, in this case, to the left, as I move in the negative x direction. So there is a little bit of increase right there. So yeah, you can kind of see it where it's below the XY plane and then it hits the XY, or it gets very, very close to the XY plane as you move this way. So yeah, this surface has no critical points. All of the points are such that near that point, there's points that are above it and points that are below it on that surface. So very um, interesting concept. So hopefully that all makes sense. So we have no critical points for this function. Now, just so that you're aware, all of the functions that I gave you were functions where we used this technique to find the critical point, where both of our first order partial derivatives had to be zero. We didn't have any examples where the first order partial derivatives were undefined. Those are a little bit more rare um, in a typical Calc 3 class, but you could get first order partial derivatives be undefined, for instance, if you were dividing by zero. So if I have something like an x in a denominator and I end up dividing by zero, or if I have a y in the denominator and I end up, there's instances in which you plug in a point and you could be dividing by zero and then get an undefined first order partial derivative. Okay. So I didn't give an example like that, but by all means, there are examples like that you could go through. So we've seen examples where there's a unique critical point. We've seen examples where there are infinitely many critical points. We've seen examples where there were a handful of critical points, like in this case, 6 critical points. We saw an example where there was no critical points. So there's no hard and fast rule about how many critical points you're going to see. Could be 0, could be 6, could be 1, could be infinitely many. But that's the nature of setting those first order partial derivatives equal to 0 and saying they both have to be 0 at the same time. Now, the other thing we can do with this technique is find maximums and minimums for a function with given certain constraints, with certain given constraints. So what we mean is a constraint means that we only allow values from a certain region. So we're going to only allow certain x values and certain y values. So far, we've essentially had functions which are defined on all of R2. And if we want to make our region a constrained section of R2, then we can look for maximums and minimums on that section. Let's do an example of this. All right. This is called optimization when we do the finding maximums and minimums. And we're going to try to find the absolute maximum and the absolute minimum of a function which is constrained to a triangular region with vertices of 0, 3, negative 3, 3, no, excuse me, negative 3, negative 3, and 3, negative 3. So we're going to find the absolute maximum and the absolute minimum subject to the fact that our points have to be within this triangle. Could be on the edges too. So let's take a look at how we would do that. So the first thing we're going to look at is to see if this function has any relative maximums and relative minimums. So we take f sub x, that's going to be 2x. We take f sub y, that's going to be 2y plus 2. And for both of them to be 0, if 2x is equal to 0 and 2y plus 2 is equal to 0, then basically we have one critical point, and that critical point is when x is 0 and when y is negative 1. So critical point of 0, negative 1. Okay. Now, here's where it gets interesting. We are constrained to this triangle with vertices 0, 3, negative 3, negative 3, and 3, negative 3. Okay, so let's take a look at that. And in particular, let's compare it to where our critical point is. So what's happening is my point 0, negative 1 is actually within the triangle. The triangle has vertices at 0, 3, at 3, negative 3, and at negative 3, negative 3. So that's what's going on. If I want to check where my function has an absolute minimum and absolute maximum on this region, remember this region is sitting in the XY plane, and above this region, there's some surface. So what I'm going to have to do is I'm going to have to check any critical points inside that region, and then any points on the boundary of that region. Now, just so you know, this boundary line is the line y equals 2x plus 3. This boundary line is y equals negative 2x plus 3. And this boundary line is y equals negative 3. Again, this is sitting inside the XY plane, and there's a surface over it, and we're trying to figure out what's the maximum point on that surface, what's the minimum point on that surface. So we're going to check the critical value or critical point, which is inside the region. If the critical point fell outside the region, we wouldn't have to check it. But we'll check that point, and then we'll check the boundaries. All right, so let's go check some things. First off, first thing I'm going to do is I'm just going to plug in the point 0, negative 1 into my original function f. If I plug in 0 in for x and -1 in for y, I end up with 0 squared plus -1 squared plus 2 times -1 plus 3. And that gives me a positive 2. So I get a positive 2 when I plug in 0, -1. Now, there were 3 boundaries that we had. Well, when we take each one, we have to basically check all the points on the boundary. There's a quick way to do that. Let's check the boundary y equals -3 first. Okay. And when we had y equals -3, that was the bottom of our triangle. That went from an x value of -3 to an x value of +3. So in other words, all of the points were looking like x value, comma, -3. Okay. Now let's think about what plugging in that point would do to my original function up here. So if I plugged in, if I plugged in a point that always was x comma -3, then I would take -3 squared. That would become a 9. And then 2 times -3 would become a -6. And so I'm getting the function x squared plus 6. I'm getting the function x squared plus 6. And we can do the same thing we did before. We can find where this function is going to have a maximum and where it's going to have a minimum between these two x values. Where is this function going to have a maximum and a minimum between -3 and 3? Well, there's the endpoints and also the critical points back from calculus 1. So if I want to find the critical points the same way I did those in calculus 1, did the same thing. Take the derivative, in this case that's 2x, set it equal to 0. X equals 0. Now, what this tells me is that I have now 3 points to plug in. One of them is the point where x is at -3 and y is at -3. Another is the point where x is at 3 and y is at -3. And another is when x is at 0 and y is at -3. So I'm going to check all of those values. I'm going to take f of -3 comma -3, see what that gives me. And then I'm going to take my function and plug in, let's say 0, -3, see what that gives me. And then I'm going to take my function and plug in +3, -3. Again, I'm dealing with the endpoints for x along with any critical value in this single variable function. So let's check all three of those. When I plug in -3, -3, again, you can just plug in to this one because all the y values are -3. So we're going to get 9 plus 9 minus 6 plus 3. That's going to give us a 15. When you plug in 0, -3, well, plugging in 0 for x, -3 for y gives you 0 plus 9 minus 3 plus 6. So, I'm sorry, minus 6 plus 3, I misspoke. 0 plus 9 minus 6 plus 3, which gives you a 6. And then plugging in 3, -3, again, just plug in there. I get 3 squared plus 9 minus 6 plus 3, which gives you a 15 again. So that's one boundary. Let's go to the next boundary that we saw. The next boundary that we saw was the line y equals 2x plus 3. And this was the boundary where x went from -3 up to 0. Hopefully that makes sense. And then we'll do the same thing for another boundary. The boundary was y equals -2x plus 3. And that went from an x of 0 to an x of 3. I want to just make sure that we're all on the same page there. So let me show you the graph once again. So we have our critical point and we have this region. And what we know is the absolute max and absolute minimum are going to have to be either at a critical point or along one of these three boundaries. We just checked this boundary here, the bottom of the triangle. The bottom of the triangle was y equals -3, and it spanned from an x value of -3 to an x value of +3. Now we're going to check this boundary. This boundary is the line y equals 2x plus 3, and it spans from x value of -3 all the way to an x value of 0. And then we'll check this boundary. This boundary is y equals -2x plus 3, and it spans from x value of 0 to an x value of 3. So here's what I do. Let's do the boundary y equals 2x plus 3. Remember, my original function, that's the one I want to use. If y equals 2x plus 3, I can replace the y with a 2x plus 3. And then that's going to give me a function that is a function that's written completely with respect to x. So I'm just going to call that my new f sub x. I guess I could call that g of x. Maybe that's a better way of writing it so that it's not confused, so that we don't get it confused with my original f, which had two variable inputs. So maybe I should do this. Maybe I should say this is k of x, and then k prime was 2x, x equals 0. This is a single variable function that I'm finding the critical value of. We do the same thing. I'm going to have a single variable function. We'll call it g, and I'm going to have a critical value of that. So let's expand this out. This is x squared plus, when you square this, you're going to get 4x squared plus 6x plus another 6x, and then plus 9. When I distribute, 2 times 2x plus 3 gives me 4x plus 6, and then that plus 3. Combining like terms, this is a pretty easy function to deal with. I get 5x squared plus 12x. Oh, no, I'm sorry, plus 12x plus 4. So plus 16x, I believe, plus 9 plus 6 plus 3 gives me plus 18. If I want to find critical values of that, I take the derivative, I set it equal to 0, and solve for x. I get a critical value when x is equal to negative 1.6. Negative 1.6 is within this region, so that means what I'm going to do is I'm going to test out 3 points. The first point is when x is negative 3. By the way, when x is negative 3, then my y value, my corresponding y value, also has to be negative 3. So I'm going to test out that point in my original function. I'm going to test out the point negative 1.6, comma, well, what do I get when I plug in 1.6 in for x? 2 times negative 1.6 plus 3 becomes a y value of negative 0.2. And then I'm going to test out what happens when I plug in 0. So my function, when I plug in 0, gives me a 3. So I'm going to test out those 3 values into my original function. Okay. Interestingly enough, I've already plugged in negative 3 into my original function and got a 15. So I know that is going to be a 15 because of earlier work. Remember, my original function was x squared plus y squared plus 2y plus 3. So if I plug in negative 1.6, negative 0.2 into that, I will get negative 1.6 squared plus negative 0.2 squared plus 2 times negative 0.2 plus 3. That gives me a 5.2. When you plug in 0, 3, 0 for x, 3 for y, you get 0 squared plus 3 squared plus 2 times 3 plus 3, and you get an 18. So I have these 3 points plugged in. Now I'm going to do the same thing with my next boundary. I'm going to replace the y with a negative 2x plus 3. And then I like to simplify and make that into a single variable function. I'll call it h this time. We're going to get x squared plus 4x squared minus 6x minus 6x plus 9 minus 4x plus 6 plus 3. So my single variable function is 5x squared minus 16x plus 18. Take the derivative. Derivative is going to be 10x minus 16. Set that equal to 0. And solve. We're going to get x value of a positive 1.6. And so that tells me I'm going to check what happens at the endpoints. I'm going to check what happens when x is 0 and when x is 3, but I also need to check when x is 1.6. So by the way, when x is 1.6, I take negative 2 times 1.6 plus 3, and that gives me a negative 0.2. So the 3 values I'm going to check are 1 is when x is 0. When x is 0, y is 3. Again, I'm just plugging in 0 there. Y is 3. Then I'm going to check what happens when I plug in 1.6. When x is 1.6, y is negative 0.2. And then I'm going to check what happens when I plug in 3. And when I plug in 3, it turns out the y value is negative 3. So that's what's going on in this case. Now, conveniently, we've already plugged in 0, 3 into this function. If you look at this, 0, 3, when we plug that into the function, we already got 18. So some of these endpoints are going to be the same. 3, negative 3, we actually plugged that one in as well. Earlier, we got a 15. And by the way, these are the same as we've already done because obviously the triangle meets up at those points. So the endpoints are going to be duplicated in certain places. The only one we haven't done is 1.6 comma negative 0.2. You can plug that 1.6 in for x, the negative 0.2 in for y. If you do that, 1.6 squared plus negative 0.2 squared plus 2 times negative 0.2 plus 3 becomes a 5.2. So this becomes 5.2, which is the same thing we got here, right? So now we have a bunch of points. And from what I said earlier, what's going to happen? Well, the absolute max and the absolute minimum are going to occur at either the critical point or the boundary points. In each of those lines, there was, well, here we've already done the critical point. The critical point gave us out a 2. Let me actually go through and write all of the points that we have. So we have our critical point, which gave us a 2. I will just copy and paste all these. 0, negative 1 gave me a 2. And then we got essentially 2 corners of my triangle along with a mid value on one of the boundaries. Then I got, again, 2 corners of my triangle along with a mid value. And then lastly, I got 2 more corners along with the mid value. A lot of these were repeats, again, because of the endpoints of the triangle. So if you look at the endpoints of the triangle, I repeated here and here. I repeated here and here. And then I repeated here and here. Now, what I claim is that the absolute maximum has to come from one of these points, either the endpoints or the critical point. So I look at the maximum output value, which is 18. That happened at the point 0, 3. And so the absolute maximum is 18, and that happens at point 0, 3. On the other side, the absolute minimum is 2. That's the lowest value that was up there. And that happens at my point 0, negative 1. So that's what's going on. That's how we find the absolute maximum and absolute minimum of a surface over a certain region. We check the boundaries of those regions. Again, in this case, each boundary gave me 3 points to check. And then we check the critical point within that region. Or if there's more than one critical point in the region, we check all the critical points in the region. If there's no critical points in the region, then we just need to check the boundaries. So that's how we approach that type of problem. So visually, when we check the boundaries, again, that first boundary, whoops, I forgot. We got 0, -3. I haven't done that. That first boundary gave me the point 0, -3, along with the two endpoints. So here, here, here. The second boundary gave me, again, the two endpoints, along with this point to check. And the third boundary gave me these two endpoints, along with this point to check. If I check all of those points, along with the critical point that we found, that we knew was going to be a relative, that was going to be either a saddle point, relative maximum, or relative minimum. If I check those points, those 7 different points, one of those has to be the absolute, one of those has to give you the absolute maximum, one of those has to give you the absolute minimum. So there we go. We're going to do one more constrained optimization problem. We're going to find the absolute minimum and absolute maximum of a function f subject to the given constraints. The function is x squared plus y squared plus 2y plus 3. Same thing we had earlier, right? Same function. But now we're going to be constrained to the region bounded by the line y equals x squared, or the parabola y equals x squared plus x minus 1, and the line y equals x. So let me graph the region we're looking at. We've already done some work with this function already, so we can reuse some of that work. And we'll check out the region that we're bounding by here. All right, so if you graph this parabola and the line, the region that we are bounded by, the region that is enclosed with those two curves being the edges, is this region in here. So this is the bounded region we're talking about. And you'll notice that the critical point of 0, -1, which we already kind of knew was going to be a critical point, that's actually right on my parabola. So that's right on my parabola. And what we're going to do is we're going to see that this region goes from an x value of -1 to an x value of +1. So if we go from -1 to +1, that's the region we're talking about. So there's two boundary lines or two boundary curves that we're going to investigate. This, which is the line, and this, which is the parabola. But we're going to investigate it from -1 to +1, x value of -1 to x value of +1. And again, remember, there's a surface that sits above this. We're just looking at the XY plane. There's a surface that's sitting above this, like straight out your computer screen. and we're trying to find the maximum and the minimum values of that surface over this region, this particular region. So let me redo what we did last time. So f sub x was equal to 2x, f sub y was equal to 2y plus 2, setting those both equal to 0 and solving. I'm not going to show that. I'm just going to state that the critical point was the point 0, -1. That's what we get if we set both of those equal to 0, forces x to be 0, forces y to be -1, right? Now let's look at the boundary. We'll start with the more difficult one to deal with. Y equals x squared plus x minus 1. And we're looking at that in between x values of -1 and +1. All right. So here's my function. I'm going to plug in x squared plus x minus 1 everywhere I see a y. Oh, excuse me. I mistyped that. Should have been a minus. Um, Trying to think if it's going to be easier to leave this section as is, or would it be easier to expand that out? I think this time I'm going to leave that as is, but I will expand, I will distribute and combine like terms with these other ones. So let me state this. So we're getting a new function in a single variable, which is giving me the exact function I have, but just on the boundary. So we get x squared plus this whole thing squared plus 2x squared plus 2x minus 2 plus 3. Combining like terms, my g of x, a little bit more simplified, is 3x squareds plus 2x plus 1, and then plus my thing in parentheses. Okay. Let's take the derivative of that. So again, we want to find critical values. And the way you find critical values, hopefully you saw in Calc 1, is you take derivative and then set that derivative equal to 0. Very similar to what we're doing here. So derivative is going to be 6x plus 2. Derivative of 1 is 0. The derivative of this is going to be 2 times the quantity x squared plus x minus 1 times the derivative of the inside function. The derivative of the inside function is 2x plus 1. Notice that I can distribute the 2. I can multiply 2x plus 1. That's less work than having to expand this out. So that's why I did it that way. So let's go ahead and do that. G prime of x is going to be equal to 6x plus 2 plus 2x squared plus 2x minus 2 times 2x plus 1. I'm going to keep simplifying till I get to something that's really easy to deal with. So 6x plus 2 plus, all right, we get 4x to the third. I get 2x squared. I get 4x squared. I get a 2x. I get a minus 4x. And I get a minus 2. This is quite a hot mess, but that's all right. 4x to the third plus 6x squared. If I take 6x plus 2x minus 4x, I get a positive 4x. And then 2 plus negative 2 gives me 0. So I'm essentially asking, when does this thing equal 0? When does 4x to the third plus 6x squared plus 4x, when does that give you 0? There's going to be a few values for x we can check, or that's going to give 0. The way I would solve this is I would factor out 2x to begin with, and I'd get 2x squared plus 3x plus 2. It turns out that this happens when x is equal to 0. This quadratic actually has no real numbers that give you 0. The solutions to this quadratic equation equaling 0 are complex. So quite nicely, the only time we get out 0 is when x is equal to 0. So the only value I need to check is the value when x is equal to 0. In other words, all I need to check here is what happens when I plug in 0, -1 into my function, along with these two endpoints, I'm sorry. So I only have one value I need to check from the middle of the boundary. I also need to check the endpoints of the boundary too. So let's plug in -1 for x. what would we need to plug in for y if x is -1? Well, along this boundary, if x is -1, you get a y value that's also -1. Just plug in -1 here. On the other side of this boundary, if x was +1, well, if x is +1, 1 squared plus, well, 1 squared plus 1 minus 1 gives you another +1. So those are the two boundary points. And the only critical point along the boundary that we need to check is the critical point that we've already discovered of 0, -1. So we know 0, -1. In our last problem, we plug that in to, again, our original function. And we got a 2. If I plug in -1, -1 into my original function, again, original function, I mean this one. If I plug in -1, -1 into that, I get a 3. And if I plug in 1, 1 into this function, I get 1 squared plus 1 squared plus 2 times 1 plus 3, which gives me a 7. Now that's the harder boundary because we had to substitute this x squared plus x minus 1 in for my y. The other boundary is going to be the line y equals x, and it is also going to go from x value of -1 to x value of +1. So let's take a look at that example. So the boundary line is y equals x, and it goes from an x value of -1 to an x value of +1. So if y is equal to x, I just replace every y I see with an x, make it into a single variable function. That's pretty easy to deal with. We get a single variable function, I'll call that h of x, which is 2x squared plus 2x plus 3. Take the derivative of that. That's going to be 4x plus 2. Set it equal to 0. Solving for x gives an x value of -1/2. So again, we're going to check the endpoints and any critical points along this boundary. The first endpoint is when x is -1. Well, when x is -1, y is -1. I've already calculated that before, right? We've already gotten that was a 3. The second value that I'm going to get is when you plug in -1/2, comma, -1/2. I'm plugging in negative 1 half, because if you plug in x of negative 1 half, y has to be negative 1 half based on the boundary condition. And then when you do that, you can plug it into your original function, or you can actually plug it into this h of x as well. These are the same two functions along this boundary. So your original function and this are the same two functions along that boundary. But either one will work. Plug in negative 1 half. And I ended up with a 2.5. And then on the other side, the boundary ends when x is 1. When x is 1, y is 1. And we've already calculated that as 7. So what we have this critical point. We saw that that was along the boundary. That was the critical point along this first boundary. Along the second boundary, we have this. The only really new point that I had to deal with was negative 1 half, negative 1 half. And so the answer to this constrained optimization problem is that the absolute maximum for the function over the region happens at the point 1, 1 and is 7. So the absolute maximum is 7 at the point 1, 1. The absolute minimum is, once again, 2 at the point 0, negative 1. So that's the constrained optimization for this example. The maximum value of the function happens at 1, 1. The minimum value of the function happens at 0, negative 1. And those are 7 and 2 are the maximum and minimum. Again, this is over this region here, the region bounded by the parabola. All right, so let me just again give you a little bit of a visual of what's going on. What we have here is our function f of x, y, and normally our function over the entire xy plane looks like this. Looks like this um, paraboloid, elliptical paraboloid. And we're trying to say, if I restrict the plane to just a section, if I restrict that plane to just the region bounded by the parabola and the line, what are the lowest points, or what is the lowest point and the highest point in that region? Highest point is up here. That happened at, well, that happened at 1, 1. We got a 7. So the highest point in that section was 7. That happened at the point 1, 1. And the lowest point happened at 0, negative 1. Let me just graph those. 0, -1, and then we got a 2. So lowest point happened there. Highest point happened at 1, 1, 7. Okay. So that's what's happening. It's saying normally I have the entire elliptic paraboloid, but we're looking at just the section of this elliptic paraboloid that's over this region. And so I check my critical points and I check the boundaries. My absolute max and my absolute min have to happen at either the critical point or a critical point or on a boundary or a critical point which is on the boundary, like in our example. So you can see that the minimum point happened at this red spot. The maximum point happened at that green spot. Minimum point, maximum point of that region. And again, this was just part of this bigger surface. This was the part of the surface that was over that bounded region. So that's the idea of this constrained optimization. We've said what is the maximum and minimum values you can get with your function, given that it's constrained to this region, that we're just focused on that, the part of my function which is above this region. And the absolute maximum, absolute minimum have to happen at critical points or along the boundaries. So we just check the critical points, check the boundaries. You can do that here as well. I didn't graph this one obviously in 3 dimensions, but we did graph the triangle in 2 dimensions. And all of this comes from a couple of things. First, if my function in 2 variables has a relative extrema at P, then P is a critical point. So we can find all of the extrema by finding the critical points and then doing a determination. And the determination comes from this rule. Those give me my relative extrema, these rules. If you're looking for an absolute extrema over a bounded region, you can just plug in. You don't have to use these rules, just the biggest point, or excuse me, the biggest output that's an option is going to be the absolute max. The minimum output that's an option would be the absolute minimum. So with constrained optimization, we don't have to use this technique, but we do have to use this technique to find all of the relative maximums, relative minimums, and saddle points. So there you go. That's this section where we're looking at extreme values. So that is the end of this video. and the end of this part of Calc 3.